Today we're going to begin talking about Chapter 6. That will be our third and final chapter in which we're covering various types of chemical reactions. In Chapter 4, we mainly worked on double displacement reactions and specifically with precipitation reactions. In Chapter 5, in addition to all of our studies of acids and bases, we learned about acid-base reactions, which are a type of double displacement reaction as well. In Chapter 6, the main kind of reaction we'll be talking about are called single displacement reactions. But by the time we finish Chapter 6, we're going to have a total of 9 different types of chemical reactions that we have covered. When we get to the end of that chapter, I'll summarize all of the kinds of reactions that we've covered in the 3 chapters, and then you'll be able to identify on a quiz or exam what kind of reaction each particular example describes. So let's go ahead and get started on Chapter 6. As I said just a minute ago, Chapter 6 deals mainly with single displacement reactions. So let's begin with those. Back in Chapter 4, we covered double displacement reactions. And in a double displacement reaction, it involves 2 compounds, AB and CD. That's why we call it double displacement, because 2 things are trading places with each other. In a single displacement reaction, we have an element and a compound rather than 2 compounds. So in this case, there's only one switch taking place. Element A is either going to trade places with element B or element C, and we'll learn in a minute how we know which one of those it's going to be. If A is a metal, then A is going to trade places with B because, of course, in an ionic compound, the metal is always the ion that comes first. So if A is a metal, it's going to trade place with metal B, and then we'll end up with metal A bonded to nonmetal C, and then metal B will end up by itself. So A is basically displaced B. On the other hand, if A is a nonmetal, it's going to trade places with C, which is also a nonmetal. You don't want to put 2 nonmetals together. You don't want to put 2 metals together. We always need a metal and a nonmetal. So in this case, A is going to trade places with C. C will end up by itself, and we'll end up with ionic compound Ba. Now you notice I wrote it Ba and not Ab. There's a reason for that, because we always write the positive ion first. So B is a positive ion, A is a negative ion, therefore it has to be written as Ba. Now let's take a look at a few examples. In this first case, our element A is a metal, so the magnesium is going to trade places with calcium, which is also a metal, and that means the magnesium will end up with the chloride and calcium will end up by itself. Like any equation that we've worked on over the last couple of chapters, we always need to make sure they're balanced and we have the physical states. In this particular case, it's already balanced because magnesium and calcium happen to be in the same group. But we still need to put in our physical states. Magnesium is a metal, so of course it's a solid. Calcium chloride, chloride has a charge of 1. It will have to be aqueous. Same thing is true with the magnesium chloride, and calcium, of course, being a metal, will also be a solid. If element A is a nonmetal, like fluorine, then it's going to trade places with the nonmetal chlorine. So the fluorine is going to end up bonded to the calcium, and the chlorine will end up by itself. You should note how I wrote F2 and Cl2. Remember, we've talked before about elements that come in pairs, the ones that are diatomic. Hydrogen, nitrogen, oxygen, and all of the members of group 7, of which fluorine and chlorine are members. Again, because fluorine and chlorine are in the same group, this equation just happens to already be balanced. For physical states, fluorine is a gas. Calcium chloride, of course, is still aqueous, as will be calcium fluoride, and chlorine, of course, is also a gas. So these are the 2 different possibilities you can have for a single displacement reaction, either metal trading places with metal or nonmetal trading places with nonmetal. A single displacement reaction is a member of a broader category which is called an oxidation-reduction reaction, or sometimes simply known as a redox reaction. Oxidation and reduction describes any reaction in which atoms are gaining or losing electrons. So the thing you can always watch for in a redox reaction is a change in the charge on an atom. Anytime you gain or lose electrons, your charge has to change. If you think back to double displacement reactions, the charges always stayed the same. If it was Fe2+ on the left, it was still Fe2+ on the right. So the key difference between single and double displacement is the fact that in a double displacement reaction, the charges never change, and in a redox reaction, the charges always change. Sounds like a couple of excellent true-false questions for a test. Let's go back and look at our initial example here, the magnesium and calcium chloride. If we want to see if this is a redox reaction, we simply need to look at the charges. Elements always have a charge of 0 when they're by themselves. All atoms begin as neutral atoms until they become part of a compound. We talked about that way back in chapter 3. The calcium, because it's now a calcium ion, of course, has a +2 charge, and a chloride ion would be a -1. So these are the charges of the 3 ions initially. On the other side, the magnesium has now become a magnesium ion, so we can see the charge on magnesium has changed. The calcium was a +2, and now the calcium is a 0 charge, so the calcium's charge has also changed. The chloride ion, its charge has remained the same. We learned back in chapter 4 that an ion that is unchanged in a chemical reaction is called a spectator ion, and that's what chloride is in this particular case. So how do we determine whether the magnesium and calcium underwent oxidation or reduction? First of all, we need to have a definition for these two things. Oxidation describes the loss of electrons, and Mark Bishop in the textbook came up, I think, with a nice little memory tool, OIL. Oxidation is loss. So anytime an atom loses electrons, it has undergone oxidation. Let's take a look at the magnesium. Magnesium has gone from a 0 to a +2. If you remember my joke I've told on more than one occasion in the videos, two atoms walking down the street, the first atom says, "I think I lost an electron." The second atom says, "Are you sure?" The first atom says, "I'm positive." The take-home lesson from that is anytime an atom becomes more positive, it has lost electrons, and therefore it has undergone oxidation. So in this particular case, the magnesium atom was oxidized. Calcium, on the other hand, went from a +2 charge to 0. So the charge on calcium actually decreased. And of course, what's another word that means the same thing as decrease? And the answer is reduce. So reduction is the process in which the charge on an atom decreases. So decrease and reduce basically mean the same thing. So we would say that the calcium ion in this particular case was reduced. Let's go ahead and take a look at a couple of more examples. This will be the reaction between sodium and aluminum oxide. And of course, because sodium is a metal, we will expect it to trade places with the metal aluminum. And that means we'll end up with aluminum and sodium oxide. And again, you'll notice that even though there was one sodium over here, we had to have two over here so we could balance the charge of the sodium and oxygen. And the fact that there were two aluminums here, but only one here, that's fine, because we're going to balance the equation in our next step. So if we balance the equation, we end up with 6 sodiums and 2 aluminum oxides, 2 aluminum atoms, and 3 sodium oxide. I'm not going to go through all the details of balancing. We spent a lot of time doing that back in Chapter 4, so that's something that you hopefully already have down. If not, feel free and go ahead and practice going through these and make sure you come up with the same coefficients that I did. For physical states, sodium being a metal is solid. Aluminum oxide, because both ions have a charge greater than 1, is a solid. Aluminum metal obviously is a solid. And sodium oxide would be aqueous because sodium compounds are always aqueous. In order to determine who's oxidized and who is reduced, we need to look at the charges. So sodium, of course, will be a charge of 0 because it's an element by itself. Aluminum in group 3, they're always a +3. Oxygen in group 6 is always a -2. The element aluminum is 0. Sodium ions are +1, and oxide ions are -2. Clearly then, we've seen a change in charges. The sodium went from a 0 to a +1, aluminum went from +3 to 0, and the oxide stayed the same, which means oxide in this particular case is a spectator ion. So, since the sodium's charge increased, we learned before that an increase means oxidized. So we would say that the substance oxidized would be sodium. The aluminum's charge decreased, and therefore the aluminum ion would be the substance that was reduced. Now there are 2 other labels that we can apply to the substances in this reaction. The sodium, we already decided, was the substance oxidized, which means it lost an electron. Well, the sodium cannot just lose an electron on its own. It's no different than if you had a car you wanted to sell. You couldn't just say, I want to sell this car. You would have to have a buyer that wanted to buy that car. If sodium wants to lose an electron, it needs someone who's willing to gain that electron. In this particular case, that was the aluminum ion. Without the aluminum ion, the sodium could not have lost that electron. So it's fair to say that the aluminum ion was responsible for sodium becoming oxidized. Or we could even say that the aluminum was the agent of sodium's oxidation, and therefore we refer to the aluminum ion as the oxidizing agent. So aluminum was reduced, but at the same time it caused the sodium to be oxidized. So those 2 terms always go together. The substance reduced is always the oxidizing agent. Now, conversely, the aluminum ion, in order to become reduced, had to find someone willing to give it electrons, and that someone, of course, was sodium. Without sodium, aluminum could not have been reduced, so we can say that sodium was the cause of aluminum's reduction, or it was simply the reducing agent. And again, those 2 terms also always go together. If you are oxidized, you had to cause the other substance to become reduced. If you were reduced, you had to cause the other substance to be oxidized. So those 4 labels always come in these pairs, and a very important point, all 4 labels are always written on the left side. Students are often tempted to think, well, I've got 4 labels, I've got 4 substances, why don't I give everybody a label just to be fair? Don't do that. The aluminum atom was not oxidized, it was not reduced. The aluminum atom is what was formed when the aluminum ion was reduced. The sodium ion was not oxidized or reduced. The sodium ion was formed when the sodium atom was oxidized. So all of the labels go on the reactant side of the reaction. Let's take a look at another example. This time we'll have a nonmetal as our element, and therefore the sulfur is going to have to trade places with the phosphorus. So we're going to end up with the element phosphorus and the compound lithium sulfide. of course, we'll need to balance the equation as we always do, and we'll want to put in the physical states. Of course, sulfur and phosphorus are both solid elements, and lithium compounds, based on the 95% rule, would always be aqueous. We'll want to go ahead and look at the charges of each of the ions. Elements, of course, sulfur and phosphorus will be neutral. Phosphide ions are always a -3. Sulfide ions are always a -2. So the sulfur's charge decreased and the phosphide's charge increased. So, of course, a decrease in charge should be reduction, an increase in charge should be oxidation, and that's exactly what we see. The phosphide ion, because its charge increased, it was oxidized, and therefore is also the reducing agent. Sulfur's charge decreased, which means it was reduced, and must also be the oxidizing agent. So whenever you work a problem like this, you've got essentially 4 things to do. Your first step is to figure out what the products of the reaction will be after the exchange. Second, you'll want to balance the chemical equation. Third, put in the appropriate physical states. And then 4, determine who's oxidized and reduced, and who's the oxidizing agent and the reducing agent. As I mentioned at the beginning of the lecture, single displacement reactions are not the only type of reactions that we talk about in Chapter 6. It is probably the most complicated one, so now we'll get into some that are a little bit easier to understand. The first of those will be something called combination reaction. As the name implies, we are combining things. For example, we can take A plus B and make AB. Now, A and B can represent either elements or chemical compounds. So there are several different possible types of reactions that illustrate combination reactions. If A and B are 2 elements, like calcium and iodine, they can combine together to form the chemical compound calcium iodide. A and B could be a compound and an element, like manganese 2 sulfide and the element sulfur, which combine to form manganese 3 sulfide. And of course, we have to make sure that we balance the equation, so we'll need 2 of our manganese 2 sulfides. The third possibility is 2 compounds can react with each other. For example, calcium oxide and water. This is actually the first chemical reaction that occurs when one makes concrete. When you take a bag of cement, which is calcium oxide, and you mix it with water, it forms calcium hydroxide. And that's the first step in the curing process of concrete. So each of these 3 represents a combination reaction. Combination reactions are pretty easy to recognize. It's the many becoming the few. Of course, they're also normally redox reactions. You can see that the calcium's charge changed from 0 to +2. Sulfur changed from 0 to -2. So a combination reaction is not always oxidation or reduction, but it is most of the time. And so that's why it will be under the umbrella of redox reactions. So now under the redox category, we have single displacement and combination. The opposite of a combination reaction is a decomposition reaction, and essentially they are just the opposite. It's a chemical compound breaking apart. So those same 3 reactions we just looked at, if we write them in reverse, they are now decomposition reactions. Now it's the few becoming the many. A decomposition reaction then joins our other 2 as a member of the redox or oxidation reduction category. There are redox reactions that don't fit neatly into any of our categories. We know they're redox reactions because their charges are changing. They are gaining and losing electrons, but they're not single displacement, they're not combination, and they're not decomposition. They don't fit that nice little alphabetic arrangement, but they're still redox. So we just use the generic term redox to describe all the other reactions that involve oxidation or reduction, but don't fit into one of those three categories. This reaction, for example, it's clear that oxidation and reduction is occurring if we look at the charges. So our iron initially had a +3 charge, and at the end it's got a +2 charge. The iron clearly decreased in charge, which means the iron ion was reduced. Sulfur's charge was initially -2. It ended up as 0. The charge on the sulfur increased, which tells us that the sulfur was oxidized. This clearly then is a redox reaction, but it's definitely not single displacement. It doesn't have the AB CD kind, or the A plus BC kind of setup. It's not combination. It's not A plus B gives us AB, and it's clearly not decomposition. So we just refer to this generically as a redox reaction. A type of reaction that we have been writing quite regularly, but I haven't actually defined it, is a combustion reaction. I've had you balance a number of different combustion reactions without actually stating that their name was combustion reactions. In general, a combustion reaction requires two things: fuel and oxygen. And our fuel is invariably a carbon-containing compound. This compound can contain also hydrogen and even oxygen. We'll take a look at an example of each of those three. Whatever your fuel is, the carbon in the fuel always becomes carbon dioxide, and the hydrogen in the fuel always becomes water. That makes combustion reactions fairly simple because the products are always the same. You don't really have to think about, gosh, what are the products going to be in this reaction? It's always going to be carbon becoming CO2 and hydrogen becoming H2O. If we have a carbon-hydrogen compound, those are the most common types of fuels. These are also known as hydrocarbons. You've probably heard that term before. So when butene reacts with oxygen, of course, it forms carbon dioxide and water. As always, we want to label the physical states in addition to balancing the equation. The butene, the C4H8, I don't expect that you guys would know what the physical state of that was, and therefore I wouldn't count it wrong either way. Whatever you wrote down there would be fine. But you ought to know that oxygen's a gas. You're breathing it right now. You're exhaling carbon dioxide, and of course you've seen water before, so if it's a compound that is obvious that you should know it, I'll expect you to list the physical states correctly. Our other possibility, or second possibility, is a carbohydrate, a compound that contains carbon, hydrogen, and oxygen. This happens to be the sugar molecule. When you eat foods that have sugar in them, in your cells, the sugar is combined with oxygen. It's essentially burning in the mitochondria of your cells to form, again, carbon dioxide and water. Now, I don't expect you guys to know from this formula that this is sugar. If you did, you would clearly, of course, know that it was a solid. But that, again, the fuels, unless it's something that's obvious, that it's a compound you should know, I'm not going to worry about whether you labeled the physical state correctly or not. Our third possibility is our fuel could just be carbon. You could take C70, which is a compound known as Buckminster fullerene, and you can burn it in oxygen. This time, of course, you only get carbon dioxide. So you don't always get water as the product of a combustion reaction. If there's no hydrogen, you're not going to get any H2O. But the carbon, of course, as always, will become CO2. There's one last type of reaction that we need to cover, and this one actually harkens back to Chapter 4 because it's a type of double displacement reaction. So this will give us the final reaction of our 9 different types that I had referred to. And then after this, I'll go through and summarize all 9 of those, and then we'll work some practice problems for each of them. If you take a look at this reaction, it looks like your basic double displacement reaction. If you wrote this out in Chapter 4, and you noticed that all 4 substances were aqueous, you would probably say it's no reaction, and normally that would be true. But it turns out that just making all 4 compounds aqueous doesn't necessarily mean that no reaction has occurred. To truly have no reaction, everything must remain exactly the same on the left and the right side of the arrow. The only way to tell for sure if nothing has changed is to write out the complete ionic equation. This, of course, is the molecular equation. That's the type we normally write. The complete ionic equation is what we get when we dissociate all of the compounds that are supposed to dissociate. For example, HBr, hydrobromic acid, is a strong acid. Strong acids, by definition, completely dissociate in water, so we would be most accurate to write the 2 hydrogen ions and the 2 bromide ions separate from each other. Any aqueous ionic compound will dissociate. That's how the ionic compound dissolves in water in the first place. So we should more appropriately write this as 2 sodium ions and 1 carbonate ion. In the solution, initially, these 7 ions are just floating around by themselves. Now we get to the other side of the equation and we ask ourselves, should I dissociate carbonic acid? And the answer is no, because carbonic acid is a weak acid. It's not on that list of strong acids. Because it's a weak acid, it doesn't dissociate, or at least only to a very tiny amount, so we would more appropriately leave the carbonic acid intact as it is. Sodium bromide, of course, because it's ionic and aqueous, should be written as 2 sodium ions and 2 bromide ions. If you get a product that's a weak acid or a weak base, or one of your reactants is a weak acid or a weak base, then it's quite likely that a reaction will actually occur. The only time you truly have no reaction is if all 4 compounds are aqueous and all 4 dissociate completely in water. And there's only 2 kinds of compounds that dissociate completely in water, and that is a strong acid or an aqueous ionic compound. If we go ahead and get rid of our spectator ions, we can cancel out the 2 bromides, we can cancel out the 2 sodiums, just like we did back in Chapter 4. We can come up with our net ionic equation. If there were truly no reaction, then everything would have canceled out here. But the fact is, we still have 3 ions by themselves on the left and a single chemical compound on the right. So there was indeed a reaction here. Now, it's not a precipitation reaction because we didn't get a precipitate. It's not an acid-base reaction because even though we had an acid, we didn't have a base. Since it doesn't fit in one of the 2 main subcategories, we're just going to leave it as generically a double displacement reaction. Just like we had a generic redox reaction, we also have generic double displacement reactions. Let's go ahead now and summarize all of the different types of reactions we've covered in Chapters 4, 5, and 6. Let's go ahead and summarize the 9 types of reactions that we've covered in Chapters 4, 5, and 6, because on a quiz or exam, I'll give you a reaction, and one of the things you'll need to be able to do is to tell me which of the 9 types it is. So let's start back at the beginning. In Chapter 4, we started out with precipitation reactions, which is a type of double displacement reaction, which has the basic format of AB plus CD, gives us AD plus CB. When you write out the balanced equation and you label the physical states, if one of the products is a solid, that's how you know that it's a precipitation reaction. In Chapter 5, we talked about another type of double displacement reaction, which was an acid-base reaction. Those are pretty easy to recognize because they have to contain an acid and a base. You guys have learned the various acids and bases back in Chapter 5, so anytime you see an acid and a base in a reaction like this, you know it's an acid-base reaction. We also learned just recently about generic double displacement reactions. They still have that same format, but in that example we went through a little while ago, if you go all the way down to the net ionic equation and you find that not everything cancels out because not everything was a spectator ion, then we have a double displacement reaction. But since it doesn't fit into the category of precipitation or acid-base, we just use the generic term double displacement. And as I mentioned a little while ago, in order for it to be no reaction, all four of the substances have to dissociate completely in water. If one of them doesn't, that's when you have your generic double displacement reaction. So all four of these compounds are aqueous. That's half of what we need. But in order to dissociate completely, each compound must either be a strong acid or an aqueous ionic compound. Nitric acid is a strong acid. Check. Sodium acetate, aqueous ionic compound. Check. Acetic acid, oops, it's a weak acid, which means it does not dissociate completely, and therefore we won't be able to cancel all of the ions out. That's why it is considered to be a double displacement reaction. And our fourth example in the double displacement category, of course, is the no reaction. And like we mentioned just a moment ago, to have no reaction, all four compounds must be aqueous and all four must dissociate completely in water. So let's take a look. Nitric acid, strong acid, dissociates completely. Sodium perchlorate, aqueous ionic compound, dissociates completely. Perchloric acid, strong acid, dissociates completely. And sodium nitrate, aqueous ionic compound, dissociates completely. By the time we have written the complete ionic equation, we can see that every one of the ions cancels out, and your net ionic equation ends up just being the arrow. So there's nothing left, therefore we know that we have no reaction. Now we move on to single displacement that we talked about in Chapter 6. It's the A plus BC type of format, but you have two different possible outcomes depending on whether A is a metal or a nonmetal. Again, if A is a metal, it's going to switch places with the other metal, B. If A is a nonmetal, it'll trade places with the other nonmetal, C. So single displacement reactions are pretty easy to recognize because they always have that A plus BC type of format. Combination reactions, again, are relatively simple. It's the many becoming the few. You can have two elements combine to form a compound. A compound and an element can combine to form a new compound, or two compounds can combine to form a new compound. In each case, we had fewer products than we had reactants. That is the nature of combination. Decomposition, of course, is simply the reverse. I took each of those three reactions from the previous example. We just write them backwards. So in combination, we're putting things together. In decomposition, we're breaking them apart. The generic redox reaction that we talked about a little while ago, if you have redox, but it doesn't fit into single displacement or combination or decomposition, we just use the broader term of redox. If we take a look at this reaction here, the cerium went from +4 to +3. A change in charge means we have oxidation and reduction, and since the charge decreased, we know the cerium ion was reduced and is the oxidizing agent. And the iron ion went from +2 to +3. That means that the iron was oxidized and is the reducing agent. So any reaction in which charges are changing, but it doesn't fit into one of the main three categories of single displacement, combination, or decomposition, just use the broad term redox. And finally, our last and sort of standalone type of reaction is combustion. Combustion reactions simply involve fuel and oxygen. The carbon in the fuel always becomes CO2. The hydrogen in the fuel always becomes H2O. And we mentioned there's three possibilities. Your fuel can be a hydrocarbon, just containing carbon and hydrogen. It can be a carbohydrate, containing carbon, hydrogen, and oxygen, or it can simply be pure carbon. So these are the 9 possibilities when you're identifying chemical reactions. Why don't we go ahead now and work through some practice problems just to get an idea of how well you understand these. For each of the practice problems in this video, you need to do 4 things. First, you need to figure out what the products are going to be in the reaction. Second, you will need to balance the equation by figuring out the coefficients. Third, label the physical states for each substance. And then fourth, determine which of the 9 types of reactions this one happens to be. So for each problem, go ahead and pause the video momentarily and then work it out on paper, and then you can go to the next slide and you can see what the answer should be. If you look at this reaction, we have an element reacting with a compound. So it has that A plus BC format, which means it's got to be a single displacement reaction. To figure out the products of the reaction, aluminum, of course, is going to form a +3 ion, therefore it's going to need 3 chlorides, and that's going to leave the iron by itself. To balance the equation, because aluminum is a +3 and iron is a +2, we would need 2 aluminums to give us 6 pluses on the right and 3 irons to give us 6 pluses on the left. For physical states, aluminum and iron are both metals, so of course they will be solid. Chloride has a charge of -1, and therefore FeCl2 will be aqueous, and AlCl3 will also be aqueous. When we only have a single substance, decomposition is really the only option. So the HBr is going to have to break apart into hydrogen and bromine. And since hydrogen and bromine are both diatomic molecules, you have to write it as H2 and Br2. To balance it, we have 2 hydrogens and 2 bromines on the right, so we would simply need 2 HBr. Hydrobromic acid would of course be aqueous, as all acids are, and from the periodic table, hydrogen is a gas and bromine is a liquid, and of course this will be a decomposition reaction. H2SO4 is of course sulfuric acid, and KOH is potassium hydroxide, so we have an acid and a base, which means it's got to be an acid-base reaction. To figure out the products, the potassium will go with the sulfate, and since potassium's a +1, we would need 2 of those to go with the sulfate, and then of course the H's and the OH's go together to form H2O. To balance acid-base reactions is pretty simple. Just make sure the H's and the OH's and the H2O's are all equal. So with 2 H's, we'll need 2 KOH, and we'll get 2 H2O. Acids, of course, are always aqueous. Potassium compounds are always aqueous. And again, potassium means this one's aqueous, and water, of course, will be liquid. With a carbon-containing compound and oxygen, we can tell this must be a combustion reaction, and so the products will have to be carbon dioxide and water. To balance the equation, we have 5 carbon, so we'll need 5 CO2. 10 hydrogens would give us 5 H2O, and then if we add up the oxygens, we have 10 O's here, and another 5, that's 15 atoms of oxygen. That would mean 7.5 O2s. Of course, we can't have an odd number or a fraction, so we simply double the coefficients and make them 2, 15, 10, and 10. For physical states, C5H10 is a liquid, but again, I wouldn't expect you to know that. But you should know that oxygen is a gas, and carbon dioxide is a gas, and that water is a liquid. With 2 elements, there's only one thing we can do, and that's to combine them, so this has to be a combination reaction. Gallium is in group 13, which means it'll form a positive 3 ion. Iodine's in group 17. It'll be a negative 1, so we'll need 3 iodines to balance out the 1 gallium. So to balance the equation, because iodine comes in pairs, we're going to have 2 galliums, and then 3 iodine molecules will make 6 iodines, and that'll give us 2 of the gallium iodide. Physical states, gallium and iodine are both black on the periodic table, so they're solids, and gallium iodide, of course, will be aqueous because iodine has a charge of 1. Okay, this reaction has the ABCD type of format, so it's going to have to be some type of double displacement reaction. Palladium, because there are 4 nitrates, has a positive 4 charge. Carbonate's a negative 2, so we would need 2 carbonates to balance the palladium. Sodium is a plus 1, nitrate is a minus 1, so it would have to be 1 sodium and 1 nitrate. To balance the equation, we have 1 palladium, 4 nitrates means we'll need 4 of our sodium nitrate, and with 4 sodiums, we would need to have 2 sodium carbonates, and now we have 2 carbonates and 2 carbonates. Everything is balanced. For physical states, nitrate has a charge of 1, so the first compound's aqueous. Sodium is a charge of 1, so this one's aqueous. In the third case, palladium is a plus 4, carbonate's a minus 2. 95% rule says this will be insoluble, and it's a solid. And then, of course, both sodium and nitrate have a charge of 1, so this one is aqueous. So because we formed a solid, this has to be a precipitation reaction. This reaction also has the AB plus CD format, so it also has to be some kind of double displacement reaction. Zinc is a plus 2, and sulfate is a minus 2, so we'll need 1 zinc and 1 sulfate. Lithium is a plus 1, acetate's a minus 1, so we will need 1 lithium and 1 acetate. To balance the equation, we have 1 zinc and 1 zinc, so that's good. 2 acetates on the left means we'll need 2 lithium acetates. And now we have 2 lithium, and we have 2 lithium, 1 sulfate, 1 sulfate. Everything looks good. For physical states, acetate has a charge of 1, so this is aqueous. Lithium is a charge of 1, aqueous. Sulfate, although these both have a charge of 2, sulfate was one of our exceptions, and therefore this will be aqueous as well. And then, of course, lithium and acetate both have a charge of 1, so this will be aqueous as well. All 4 compounds are aqueous, they're all ionic and thus dissociate completely, which means we have no reaction. that completes our study of Chapter 6. So Chapters 4, 5, and 6, as I've said before, all have basically the same idea, which is various kinds of chemical reactions. By the time we've made it now through Chapter 6, we have a total of 9 different types of chemical reactions. Because there was a lot of material on these 3 chapters, I'll be dividing it up into 2 quizzes, quiz 4 and 5. But in both of those quizzes, you're going to need to understand all of those various kinds of chemical reactions. So I will be giving you examples. You'll have to complete the reaction, label the physical states, balance the equation, and tell me what type of reaction it is. And then next week, we'll go ahead and start our next unit. We're going to be learning all about energy, because energy is important in all chemical and physical changes. Energy is always involved in one way or the other. We'll talk about that next week.